So our goal is to learn how to classify a set of training samples xi with labels yi, and yi here can take two different values. So this is what we call a binary classification. Okay, so we have two classes, right? So the goal is to find, as you guys remember, the hyperplane that, or the decision boundary that separates these two classes. And I would say the story of SVM starts with what we call a dot product. If you guys remember, what is a dot product? So a dot product, so let's say we have our initial point. So this is maybe the origin. Let me just move this a bit down. Right, so this is our space, the origin of our coordinate system. So this is sample x, right? And then what we have another vector. Let's define a vector w. And a dot product, if you remember, a dot product between x and w in linear algebra. So let's say for the sake of simplicity and in this example, w has two components, so both belong to R2, right? So x, the dot product between x and w is x transpose w. And here if we transpose it and do the multiplication, so we have x1, x2, right, times w1, w2. And we just, multiply those. So it's like x1 w1 plus x2 w2, and this is exactly the dot product between these two vectors. Now geometrically we have a more interesting things to say. So what does that mean? So here, this is basically the projection. It's related to the projection of the vector x onto the direction or the vector w, right? So the projected vector is, let's say it's this one, has a specific length L. And in linear algebra, there is a formula. We know that xtw, the dot product between these two vectors, is equal to L times the norm of W, okay? So this is the dot product rule that drives a lot of problems in machine learning, whether dimensionality reduction, feature selection, all these problems that we'll learn about later on. So this is very important. Now, why it is important? Here, if you guys remember, when we defined our hyperplane, so this is, for example, let's just, okay, so I'm just gonna draw it right here. This is our hyperplane. It's parameterized. It's by this equation, right? So all the points that satisfy this equality, they belong to this hyperplane. And we know that W is actually the perpendicular vector, the normal vector to the hyperplane. Okay, it's the normal vector to the hyperplane. So what do you guys notice here? So if we have a point, now let's go back to our classification problem. So this is our point X, and we have more points, right, on this side of the plane. And we also have other points, or data points, falling on the other side of the plane, right? So if you know this, what we want that all points that fall on this side of the plane, that's called the pink side, okay? So we want all those points. We want the dot product. Basically, we want them to be greater, so xtw, greater than a constant c. So why is that? What does that mean? It means that I want them to be far away from the plane. So I want them to lie far away within a distance that's larger than L, like within a specific margin, right? So all those points, if I project them, they will all satisfy this inequality, right? And the other one. So all of those you can see that they should lie like far from the plane, so on this side. So these points, the positive points, satisfy this inequality. Now there's another thing where you guys know this too, if you notice. Here, if we project this onto the vector x onto the vector w, so the length L here is exactly, if we project it right there, it's the distance from the point x to the hyperplane. So basically what we want to do, we want that, if we forget about the b for a moment, okay, the bias, we want that this point, we want it to lie on the right side of the plane, far from the plane, the hyperplane itself. Now for the other points, right, so you know that if we project this point onto the w vector, so this is our w, right? So here we have an angle that's greater than 90 degrees, so we will have a negative, so L here will be negative, so we'll have a negative value of L, but still, like this is, you know, the projection. So what we want to do, we want for xt, we want for each point on the other class xtw to be, you know, smaller than a specific constant c, okay? So we want them all, because in this case they're all negative, so it's the other condition that we need to satisfy. And if you guys remember, this is exactly what we found last time when we talked about perceptron, but from a different perspective. We did not really talk about dot products, but it's all based on dot products. Now, something more interesting. So let's look at a point. If a point x belongs to the falls or lies on the hyperplane itself, then what we have the dot product between x and w. Now it's getting too colorful. So and w, right? So we have a 90-degree angle between them, so they're perpendicular. So the dot product between these two is equal to what? If x belongs to lies on the hyperplane, is equal to 0. And this is exactly the equation of the hyperplane. So we know how to find all those, how to define a hyperplane by finding at least, you know, like a few points that satisfy this equality. Okay. Now going back to our case, this is, you know, exactly what we want to do. So here, we have our points or our vectors belonging to this class, and also the data points belonging to the second class, right? And what we want to do, we want to classify them. So here, let's say this is the hyperplane that maximizes the distance between these two classes. Right, so if we take the W, so the W will be perpendicular to this one. So maybe this is our W. So this is what we want to do. We want, if we project, so just to sum up, if we project all those on the W, we can see that they lie on this, on the, below the hyperplane, in this part, right? And then if we project the other ones, like the other points on the W, okay, so this is the projection, all those. So we can see that all of them should, this dot product should be very large, okay? So for these points to lie far away from the plane, but on the other side, okay? Great, now let's look at this particular case. So here, what do we have? We have two particular points. We call them maybe marginal or extreme points. So we have x1 that lies on the translated version of the hyperplane, so by +1. So this is, let's call it the upper hyperplane. And we have another point lying on the boundary, on on the second boundary or the bottom hyperplane. So here what we want to do, remember guys, we want to correctly classify all points, but at the same time we want the distance between these 2 points. We want the margin or the space between these 2 classes to be large. So let's say this is our the origin of our space. So we have point x1, or it's a vector, right? So when I say point, it means a vector in our case, and to generalize more, in x2, right? And we know that x1 minus x2 is this vector. A bit of geometry, right? Right, so now if you look at this, if we dot x1 minus x2 with w, the vector w, what do we get? So here, if we dot it with w, we can see that the projection of, select another word. So if we project it, we dot it with w, so we have x1 minus x2 transpose w is equal to what? To L. So L is the length of the margin that we want to maximize, right, between the 2 classes, times the norm of W, okay? So our goal in support vector machines is to maximize the margin. So to maximize the margin, the first step that we want to do, we want to compute the margin, okay? So L here is equal to what? So I would give you guys like a minute, and I would like you to take maybe pause this video, right, and try to derive the formula for the margin L. And for that, you have 2 hints. So basically, you know that x1 satisfies this equality, and also x2, because they lie on the boundary, okay, of the bottom hyperplane and the upper hyperplane, okay? So just take a minute and try to compute L. Okay, so here, let's do this together. So x1, so we know that x1, so let's write it down. So L is equal to what? To x1 transpose W plus x2 transpose W, and we need to divide by the norm of W, okay? So if we expand this, we know that x1 W is equal to what? To 1 minus B, and x2 W is, so here, right, so there is a mistake, so here it's a minus, right? We have a minus right there. And minus x2 W, minus x2 transpose W is equal to B plus 1, so but plus B plus 1. And we divide it by W. So here, what do we find? We find that if we remove those, it's equal to 2 divided by the norm of W. So this margin right here that we want to maximize is equal to 2 divided by the norm of W. And what is W? W is the normal vector, right? It's the normal vector to our hyperplane. So what you guys need to remember is that here it's very interesting because the W tells us about 2 things, right? It tells us, it specifies the direction of the hyperplane, where the hyperplane lies exactly in our space, its position, right? But also it specifies the margin that we want to maximize. So W as a vector, it locates the hyperplane in our space, but its norm, its magnitude, its strength, it defines the margin between these 2 different classes, right? So this is quite this is very interesting. So you need to remember that W is like everything is basically encoded and defined and driven by W in this case, right? So here, what we have, so this is exactly what we have solved, and we found that L is equal to 2 times the inverse of the norm of W. So our goal, let's remember again, so is we want to maximize the margin, right? So we want to maximize L, find the, let me just, okay, so we want to basically find the optimal W that maximizes L of W, and L of W is the length of the margin, okay? It's the width of the margin that we want to maximize. So here, it's if we want to maximize this problem, like this basically, we want to maximize this loss function. Somewhere we don't call it loss here, so we can call it the cost function, right? We want to maximize it. So alternatively, if we want to turn this problem into a minimization problem, then we would take just the inverse, right? So that would be half of the norm of W. But as you guys notice, now this is the problem that we want to solve, right? This is a non-convex problem because we were just taking the norm of W. So we want to convexify it. So the easiest way is to take the squared norm of W, and this is for mathematical convenience, right? So this is the loss function that we want to minimize, right? So this is part of the SVM loss function that we want to minimize. But would this be sufficient? Is this enough? Like, let's say if we solve this problem, we will find everything. We will find our hyperplane, we'll find our margin, and we're good to go. So if you guys think about it, let's look at this problem. So if you want to minimize this, we know that this is always positive, right? So what is the minimum value that this function takes? It's 0, right? Because if we have W equals to 0, that's its minimum. So we have a trivial minimum for this convex function, right? So if we have W equals to 0 everywhere, so this is a vector, right? It means we have no hyperplane, we have no margin, and it's like, yeah, so this is a problematic case. So if you guys remember, what we want is not just to maximize the margin. We want to, maximize the margin. We want to maximize the margin, and at the same time, we want to correctly classify all those points, right? So we want them to lie on the right side of the plane. We don't want to make mistakes like that, okay? So to do that, remember, there is another condition that we need to add, and this is the condition, right? So we want to minimize the this loss function constrained to the condition of, the constraint of correctly classifying our training points or our training data for each point I, okay? So this is what we call a constraint optimization problem, and this is how we formalize it. So we want to basically minimize a loss function L of W subject to this condition that we can call, so like this function here, we can call F. So we want F of W. So for now, we're just kind of overlooking the B, but we want F of W be all parameters that we want to estimate to be smaller or equal to 0 for all points I. So we have Fi, okay? So this is the constrained optimization problem for SVM. Okay, great. So getting to this point, now we want to look at this question, right? So this is what we call the hard margin SVM problem, okay? And we will look now at two different cases and try to understand why SVM classifier will not settle for a small margin for linearly separable sets. Why it will not, stop at a small margin. If it can still maximize it, it will maximize it. Right, so let's look at these two cases. So first, for example, here what we have two different data sets, the blue dots and the red dots. So let's say, for example, this is the hyperplane that separates these two classes. So this is, when we're like, SVM is basically iteratively trying to move this hyperplane and find the one that maximizes the margin and at the same time correctly classifies these points. So maybe at some specific or particular iteration, it's stopped here, okay? So let's look at this. Now, what we have, remember, the secret is in the dot product. So this is basically the W, which is the normal vector to our hyperplane. And we have our points. So for example, our point x1, okay, so that's our vector. And if we project it, we will see this, let's call this L1, okay? So that's the length of the projection of x onto W. Now for, let's choose another point, x2. And we also project it on the W. So here we have L2. Now what we want to do, so we see that in this case, the margin is defined, is confined to this, within this space, right? Okay, now let's write this down properly. So for convenience, to simplify things, we're just gonna remove the B. So let's say x1 t w, the dot product should be greater than 1. Okay, so this is the margin perceptron condition. And here, this is the equation for this plane, right? So in this case, what this means, it means that we want L1 times the norm of W to be greater than 1. And since L1 is quite small in this case, right? So it's not large. So we would, to maximize this, to make it larger, much larger than 1, then we need to boost the W. So we need to maximize the W because the L is small, okay? So this is counterintuitive because our goal is to minimize the norm of the W, not maximize it. So SVM will not basically stop at this, right? So now if we look at the other scenario here, let's say this is the hyperplane, the optimal hyperplane. And let's do the projection again and compare. So we're projecting this point x1 onto the W. So this is L1. So let's just use the same color. So this is L1, okay? And then we project also x2. So here what we have is L2. And what do you guys notice? Like, just by comparing, this is a so this is a larger margin, right, between the two classes. Here it was quite small. It was quite confined, right, to the space. So this is a better choice for SVM. Why is that? If we write it down, so the condition is the same. So we want basically we want x1 transpose W, the dot product, to be larger than 1 for the positive class, right? So this means that L1 W is larger than 1. So if L1 is quite large, is very large, right? Then our goal, then we can minimize this. So we should minimize this to make it larger than 1. So we need to kind of tone it down. And to tone it down, we need to minimize the W. Okay, so I guess that's it. And in the next video, what we'll do, we will just look at how we're going to solve this problem.